Hello. Today I will talk about a recent paper wrote with Professors Dave Kaiser and Evan McDonough on natural inflation with an exponentially small tensor-to-scale relation. And after a lightning fast introduction, I will discuss our model in some detail to then move on to discussing what the prediction, especially the observables of this model are and what the consequences of this may be. Let's start by talking briefly about inflation, which, as you probably all know, is a very short epoch of extremely fast expansion of space taking place in the very early universe that was first introduced in the 1980s to solve some outstanding problems in hot Big Bang cosmology. And it is now also a mechanism for production of large-scale structure and of the standard model particles. Furthermore, it can also serve as a production mechanism for possible model candidates of dark matter. So inflation is very well tested against observations so far. In particular, for example, the observation of baryonic acoustic oscillations proves that there must be a primordial power spectrum, such as the one predicted by inflation, as opposed to theories like cosmic strings that do not predict one. And in its simplest realization, inflation is driven by a single scalar field called the inflaton that is minimally coupled to gravity through the Einstein-Hilbert action, as shown here, and lives in a potential that has a shape like this one, so that our scalar field rolls down the slope of this potential, and as it does, it generates this this exponential expansion of space. Now, one of the first models of inflation that was introduced in the 1990s is built on the idea that the scalar field, the inflaton, is none less than an axion. That is the pseudo-Nambu-Goldson boson of a spontaneously broken U1 symmetry. And this theory can be described by a complex scalar field that has a radial component and a phase, the phase being the actual axion field. This field, the axion, gains a mass by further explicit breaking of the U1 symmetry through non-perturbative effects, generating a potential of the kind shown here. Now, if we take this potential to be the potential of inflation, we get what's called natural inflation or axion inflation. However, nowadays, if we look at observational constraints, these are by the Planck collaboration, we see that this natural inflation model, which is shown in this purple region, is not compatible with the strictest constraints by Planck. So this is the plane of the tensor-to-scalar ratio versus primordial tilt that we will define later. Suffice to say that this seems to suggest that natural inflation is not compatible with observations. However, let's jump to nowadays and introduce multi-field models. So first of all, what does that mean? It's models where instead of having only one scalar field having inflation, we might have more than one. And the reason is that we know in the universe there are multiple scalar fields. For example, even the Higgs in the standard models comprises 4 scalar fields. So this brings the question of why should only one of them, one scalar field, be responsible for inflation? Furthermore, axion models are inherently multi-field theories because, as we saw, they describe this complex scalar field that has two scalar field components, the radial one and the axion one. So what we will do here is to not only consider the evolution of the axion field, but also the one of the radial field in inflation. So this brings us to multi-field natural inflation, which can be described from through an action of this kind, where we now have 2 kinetic terms, one for our radial field and one for the axion, which also is coupled to the radial field. Now, introducing the radial field can also allow us to have non-minimal coupling of this latter field to gravity. Now, the axion field by construction is not subjected to perturbative breaking of the U1 symmetry, and thus needs to be minimally coupled to gravity. But the radial field does not need to satisfy that. Now, this coupling at the end of inflation, so once the radial field will have completely decayed to a value V, needs to be equal to the Planck mass. The last term in this action is the potential, which has 2 terms, the second one is the axionic potential that we saw earlier. And the other one is the spontaneous symmetry breaking potential, the Higgs potential, if you will, upon which the radial field will be subjected to. Before moving on, I wanted to mention that the axion decay constant in this model becomes dynamical. So it evolves in time as opposed to being a constant through its evolution. So this is the form it takes in the Einstein frame. So let's now look at the background dynamics of the system. So solving the equations of motion and the Hubble Friedmann equation for this model, we will see that we get an additional friction term in the equation of motion for the axion field that will basically force it to be frozen at early times while the radial component, the radial field, decays. So this is the evolution in time where inflation ends on the right-hand side at n equals 0 of our system. And as we said, we see that the radial component evolves first in this phase 1 of inflation. We then get a phase where actually both fields contribute to the dynamics, which is shown here by the evolution of this red curve, which is the fraction, the energy fraction of the axion fields with respect to the total one. So at first it's almost 0, and then it becomes almost just above 1/4. So in the second phase and third phase, both fields contribute. What is interesting is that at the boundary between phase 2 and 3, we see that the axion field starts decaying. So this will, as we will see in a moment, create a turn in the field space. The last thing I wanted to mention is that the Hubble parameter is very tiny. So again, we see that there is a first decay, then a plateau, and then another decay of the Hubble parameter. But this is magnified by 10 to the 12. So we have the Hubble parameter of 10 to the minus 12, which is lower than what we usually have in inflation. So this is low scale inflation. Now, moving on to considering the perturbations during inflation. Now, since we have multi-field dynamics, we don't only have perturbations along the field's trajectory, like we have in a standard single field inflation, but we also find perturbations perpendicular to this trajectory. So we showed here in this 2D plane, characterized by the direction of the two fields, a trajectory where we have these R curvature or adiabatic perturbations along the trajectory. These are perturbations that affect the total energy density of the system. But we now also have these isocurvature or entropy perturbations that modify the ratio of particle species, but not the total energy density. And an important thing to notice here is this parameter, the turn rate, omega, which describes how the field trajectory in field space changes in time. The reason this is important is because when we look at the equation of motion for the curvature and isocurvature perturbations, these are coupled through this turn rate omega. In particular, on large scales, on super Hubble scales, the equations of motion are reduced to the two shown here. And we notice two important things. The first one is that the curvature perturbations are now not conserved on super Hubble scales. In particular, R can be sourced by an isocurvature perturbation when the turn rate is non-zero. And the second thing we notice is that if we consider this μs to be the effective squared mass of the isocurvature modes, the isocurvature modes grow when μs is tachyonic, and they decay when μs is large and real. So looking at that, let's first have a look at the turn rate, which, as we said before, we expect to be large when the axion field starts decaying. So at that point in time, we transition between phases 2 and 3, as we defined them earlier. We have a turn in trajectory from going to along the radial field direction to another direction that comprises the axion direction as well. So it is 0 for all time and then peaks at that boundary between the two regions. Looking at the evolution of the effective mass of the isocurvature modes, we see that it is small but real at early times. It then, during phase 2, quickly decays and becomes tachyonic. It produces a tachyonic instability. And eventually, at the boundary between phases 2 and 3, goes into a real mass very quickly and becomes positive. So this translates, if we look at the evolution of curvature and isocurvature perturbations for single modes that exit the horizon or rather Hubble radius around 50 equals before the end of inflation, we see that the isocurvature indeed is almost frozen, but slightly decays during phase one. It then quickly goes sourced by this isocurvature tachyonic instability, and then eventually decays during phase three as its effective mass becomes real. And the other interesting thing we see here is that the curvature mode in blue gets enhanced super horizon, super Hubble by this very isocurvature mode. So when the turn rate is non-zero, we have this transfer of power from the isocurvature to curvature mode. And this can be characterized through the transfer function TRS. So shown here is actually the power spectrum of the two modes. And when we consider the value of this power spectrum at the end of inflation for a series of K modes, we can find the overall curvature power spectrum, from which we can define and determine the different observables of this model of inflation. So moving on to observables, first of all, I want to more accurately define the tensor-to-scalar ratio that we have mentioned. What is it? It's the ratio of the amplitude of the tensor modes to the amplitude of the scalar modes produced during inflation. The ones we considered so far, both curvature and isocurvature, are scalar, and we saw that R gets enhanced. But during this time, the tensor modes are actually unaffected by the background dynamics and even by the turn rate and enhancement of the curvature perturbation. This is because they follow this equation where K is proportional to A HK. And when we solve this on large scales, super Hubble, we see that UK is proportional to A, and therefore H is just constant. So the tensor modes are unaffected by the dynamics. While these modes are unaffected, and therefore the amplitude as well, we saw earlier that the scalar amplitude of scalar modes is vastly enhanced. So therefore, the tensor-to-scalar ratio is vastly suppressed by this enhancement of the curvature perturbations. So much so that it gives us value of order 10 to the minus 16, which is much smaller than current bounds on this value. So we need to look at something else. The spectral index, which is basically the slope of the curvature power spectrum, and the running of the spectral index, alpha s, which is its first derivative. So let's go back to looking at the NSR plane, which is what we looked at in one of the first slides from the Hubble constraints, Planck constraints, which we have reported here. So as we mentioned before, the tensor-to-scalar ratio of this model is extremely small, over the 10 to the minus 16, as opposed to constraints which are currently ordered to 10 to the minus 2 or 3, and which might not become smaller than 10 to the minus 4 anytime soon. So these are the predictions of the Simons Observatory. At the same time, our values for NS are compatible with current and future observational bounds as well, as shown here. One thing to notice here, we expect our CMB modes to exit the horizon around 49 e-folds before the end of inflation. That's because we have a small scale inflation. And also in these models, the reheating is very efficient. So we only expect our uncertainties on N star to be plus or minus 2.5. Now, what this suggests is that we cannot test such a model through the tensor-to-scalar ratio or through the observation or non-observation of the B-mode polarization of the CMB, which is usually considered to be the next observational frontier from the inflation. So how do we test this? We suggest doing so through another observable, which is in fact the running of the spectral index alpha s. So when we look at the NS alpha s plane, we see indeed that our model can be tested and even completely ruled out by next generation observations. So we have here the CMBS4 and Sphere X experiments and their combined expected bounds. And in fact, with this, we could fully rule out this particular model of inflation. So while we cannot test it with B modes, we can test it through the running of the spectral index. And one thing that is interesting here is that while CMBS4 will look at the CMB, the SphereX actually looks at large-scale structure. So the combination of these two methods can be extremely powerful. And before moving on, I just wanted to quickly mention that there has been some other interest in alpha S, also in the case of single field inflation, for example, in the work of professors McDonough, and McDonough. Before concluding this talk, I just wanted to mention that the isocurvature fraction and the non-Gaussianities produced in this model are extremely small. In particular, since the isocurvature modes we saw decay at the end of inflation, their isocurvature fraction at primordial times and therefore late times is extremely small. In particular, it is of order 10 to the minus 15, while observational bounds are of order 10 to the minus 4. Similarly, because of suppression of high K modes in the curvature power spectrum, we expect the B spectrum to be peaked in the equilateral configuration. And when we compute numerically the value of FNL in the equilateral configuration, we get a value of 0.48. So that's quite small. So to conclude, I want to say what we found here is that natural inflation can again be compatible with current data and future predictions once we include the dynamics of the radial component of the complex scalar field. So when we include multi-field dynamics. And in such models, we can find that the tensor-to-scalar ratio can have extremely small values while keeping the value of the running of the spectral index non-zero. This suggests that inflationary models that might not be discoverable through the observation or non-observation of B modes in the CMB could, however, be tested through this other observable, the running of the spectral index, which we suggest as a goal for next generation observations. And in the future, we will explore parameter space in more detail to confirm our predictions and perform an analysis of the mu distortions of the CMB produced by this model of inflation. So thank you very much for your attention. And I look forward to any questions you may have and hopefully be able to answer them and to any discussions this may bring about. Thank you very much.